the monitor implementation that we were looking into. So, we have seen that there are two gates. One is that one gate was that mutex gate. Okay. So, one gate was that mutex gate, and the other gate was that next gate. Okay. So, this is the mutex gate and this is the next gate. And apart from that, what we have, so this part is fine, like when a process is finishing a routine here. So, this at the end of this routine, it is checking whether somebody is waiting at the in this line. So, then that is made to enter into this monitor, or if nobody is there, then it is making somebody from here to enter into the monitor. So, that part is fine. So, what is left now is the condition variable. So, next we will see how these condition variables are implemented in this particular structure. So, for that we can implement this condition variable like this. So, we have got a number of condition variables. So, this next becomes a queue like this, and we have got a number of condition variables, say 2 condition variable x and y, and there are some queues with that. So, how these condition variables are implemented? So, for each condition variable x, we have got a semaphore x same, which is initialized to 1, and we have got an x count, which counts the number of processes which are waiting on this particular semaphore. So, any process which is trying to call an wait operation on this condition variable x, that is the x dot wait function. So, it is it is implemented like this. So, we have got this x counting the x semaphore, the condition variable x, which has got an associated semaphore x m and this count. So, first this count is incremented. So, I have a process in its execution. So, somewhere here, so in some code here, it has given a call to x dot wait. So, this is the procedure f, and in that there is a call to x dot wait. So, how this x dot wait is implemented? So, it is implemented like this. First of all, we increment the number of processes waiting on this particular condition variable x by this x count plus plus, and then after incrementing, what it has to do is that it has to give a call on this semaphore x m. It has to wait for on this semaphore x m. But so, basically it has to go out of the monitor and it has to wait on the some other process to give it a signal. Okay. So, but before going out, so as we have discussed previously, before going out it must check whether somebody is waiting in this next queue. So, that process is put inside. So, that is done by this pair of statement. If next count greater than 0, then signal next, otherwise it can signal somebody from this mutex entry. So, signal mutex. So, this is basically the exit part, I can say. So, the process has incremented the count, after that it will give a call to wait on x m. So, then that means it is its job is done, but in between the process wants to go out of the monitor, and for that before going out it has to execute this piece of code for allowing other process to enter into this monitor, either some signaling process that is waiting here or a new process from this side. Now, the process is waiting on this. Now, after some time what will happen is that some other process will execute a signal statement. Okay. So, some other process which has entered from here or from here. So, that will execute a signal on this x condition variable. So, that is it will execute some x dot signal statement. We will look into the implementation of x dot signal slightly later, but suppose this process wakes up. Okay. So, when this process wakes up, so somehow this count variable has to be decremented, because this x count. So, now this process will be will enter into the monitor. So, it was waiting at this point. So, it is again entering into the monitor, and then it will be continuing from here. So, for that purpose it decrements x dot x count and proceeds from there. Now, if we see the signal part. So, you see the signal part is implemented like this. So, this x count is, if x count is greater than 0, then it has to go out of this semaphore and it go out of the monitor, and it has to signal some process which is waiting on this condition variable x, and that is done by this. So, this next count plus plus. So, this is actually the process will be going out from this. So, the signaling process will be going out through this next line. So, that is why it has implemented this next count. Then signal xm. So, signal xm. So, this will be signaling the waiting process. Okay. So, this on this condition variable x. So, this will signal that process, and then it will wait for next. So, the wait for next will take the process out from here, and it will be waiting in the next queue. And then again after some time some other process, when it finishes, so it will check whether next count is greater than 0 or not, and then it will be again taking the process inside, and at that time this process wait will be over. So, it will come to this point and it will be executing this next count minus minus. So, next count will be decremented. So, it is a, you see, it is a collaborative implementation of number of processes, their execution sequence, like how they will be done. This the semaphore, the monitor boundary, and this individual functions that we have, individual access routines that we have, and the wait and signal calls. So, everything are used together, so that we can get this whole thing implemented and a proper synchronization is done. So, you just think over the whole issue and take all of them together, then only you will be able to understand the bits and pieces, they will fall into their proper places. So, this is how this monitor can be implemented using semaphore. It is a bit complex concept, but I think you just think it in a cool mind, and then you will be able to get it. Now, if you want to resume processes within a monitor, if several processes are queued on the condition variable x and x dot signal is executed, which one is resumed? So, this is a problem, like I have on this condition variable x, we have shown that there are number of processes waiting on this condition variable. So, which process will be resumed? The strategy that we have discussed so far, it does not tell anything about which process will be resumed. So, naturally there is a question of starvation. So, FCFS is frequently not adequate, first come first served may not be adequate because of the reason that there may be priority. Conditional wait construct in the form of x dot wait c, where c is a priority number. So, that can be used. So, if the processes have got some priorities, so we can put that priority into this x dot wait call, so that this priority is taken care of. So, process with lowest number is scheduled next. So, the number is low, we mean that its priority is higher. So, the process with the lowest number, so that is given the highest priority. Some languages provide a mechanism to find out the PID of the executing process. In C, we have got get PID type of function, which returns the PID of the calling process. So, this returns the PID of the calling process. So, that way we can issue the priority number of that, get the priority value of that. So, this is possible. Next, can have a resource allocator based monitor. So, monitor to allocate a single resource among competing processes. So, this is a situation where we have got a monitor that is used to allocate some resource, and this is the way this is implemented. So, we have got a monitor resource allocator, and in this we have got this boolean variable bz and this condition variable x. So, they are internal to the monitor, they are not visible from outside. This acquire and release, so these are two functions that are available from the from outside the thing, from outside the monitor. So, we can have a look at this. Now, this outside routine, so it can give a call to this acquire. So, any process when it is requesting an allocation of the resource, it specifies the maximum time it plans to use the resource, and for that time the monitor will allocate the resource to the process that has the shortest time allocation request. So, it is assumed that we have got this type of strategy, that whenever a process say P I wants to access a resource, so it tells for how much time it needs to access the resource. So, in the code of P I, maybe it is giving a call to acquire 10. Okay. So, what is happening in the acquire routine? So, if the resource is not busy, then it is immediately allocated, but if it is busy, then the process is put into the corresponding condition variable wait state. So, x dot wait, and in the condition variable for x, so it is put into a queue like this, and since if some other process p j also comes, and that is that also makes a call to this acquire, and that requires say for 20 time unit, then this process p I is placed first, then process p j, like that. So, whichever process has got less resource utilization time, so that will be given priority. So, another process p k comes. So, p k says that I want to acquire the resource for 5 time units. So, this list will be modified, so that p k comes here, p I goes there, and p j goes at the next place. So, that way this queue has to be manipulated, and this that can be done very easily by checking into the corresponding values of this semaphore of this condition variable. So, we can check where it should be put. So, if a process is acquiring the resource, so it is doing like this. Similarly, release the resource. So, this is made by making busy equal to false and calling this x dot signal. So, we assume that x dot signal, it returns the first process from this queue, and this queue is already sorted based on the timing value of this resource utilization. So, we can say that this will be taking out the process which requires the resource for the shortest amount of time. So, it is trying to follow that shortest job first type of policy, but with the assumption that the process themselves tells like how much time it needs the resource. So, and there is an initialization code which is busy equal to false. So, this particular statement, this busy equal to false. So, this is the initialization code for the monitor. So, when this monitor resource allocator is created, so these variables are created, and this busy is initialized to false. After that, any process asking for the resource, so it will be calling this acquire routine, and similarly for releasing the resource, so it will be calling the release routine. So, this is how this monitor can be implemented. So, a process that needs to access the resource in question must observe the sequence like this, that r dot acquire t. So, it will be trying to acquire the resource, then access the resource, then r dot release. So, it will try to release the resource. So, that way it can call that acquire and release functions from the resource allocator monitor, and accordingly it will be executing them. So, we can have this resource allocator implemented by means of monitor. So, observations like incorrect use of operations, like again the type of operation that we can have, the incorrect sequence may be first a process gives a call to release, and then it gives a call to acquire. So, this acquire release call sequence, so that is just reversed. So, unlike this thing, so this is this acquire release call. So, instead of the r acquire first and release next. So, maybe it is just these are just reversed. So, that way we can have a problem that release and acquire reversed. Similarly, the user may make a mistake that instead of calling release may call acquire again. So, that is acquire type of sequencing, or another possibility is omitting acquire and or release or both, maybe for forgetting to put this acquire or forgetting to put this release. So, this type of things can happen, but they are not that much severe compared to that semaphore based implementation. So, monitor we can always check whether it is there or not. The solutions can be there, but it is going beyond the scope of this course. So, we will not go into that discussion. So, to conclude this discussion that we have made so far, so mutual exclusion must be provided between cooperating sequential processes. User coded solutions are primitive. So, semaphores may be used, and higher level primitives like monitors may be used for this purpose. So, these are the things that we have learned so far. So, next we will be looking into some synchronization examples, and we will see how they can be solved using these semaphore based solutions. So, first we will take an example, which is the problem statement is like this, that we have got say there is a round table. Okay. So, this table, so this problem that we are talking about, so this is in popular this is known as cigar making example, and my objective is not to promote smoking and all, but I am just taking this as a as an example problem. Okay. So, to make a cigarette and smoke, so what is required is that we need some tobacco, need paper and lighter. Okay. We need tobacco, paper and lighter. Now, we have got 3 smokers sitting here, smoker 1, smoker 2 and smoker 3. Smoker 1 has got infinite supply of tobacco and paper. Smoker 2 has got infinite supply of paper and lighter, and smoker 3 has got infinite supply of tobacco and lighter. So, none of them can individually make a cigar and smoke. So, because of the third item is not present, fine. And there is another agent. So, this agent does not smoke. So, agent has got infinite supply of all the 3 items like tobacco, paper and lighter. So, what the agent does is that randomly picks up one of these 3 items and puts it onto the table. Suppose the agent puts tobacco here. So, as a result this smoker 2 will be able to get it, make a cigarette and smoke. Then after that agent takes off this tobacco and places again randomly one of the 3 items tobacco, paper, lighter onto the table. Suppose puts a lighter here, then this tobacco, so now this smoker 1 can make a cigar and smoke. So, this way I have to we have to give a solution, we have to model this particular problem in terms of a synchronization problem. Okay. So, how do we do this thing? Okay. So, for doing this, so we can write down the code for smoker 1. So, I assume that this is an infinite loop. So, while true do, so this smoker 1, so they has to wait for the lighter. So, wait for, I assume that there is a semaphore light same on which this smoker has to anybody waiting for this lighter will be waiting on this light semaphore. Then it will be calling make cigar and then okay, let us make it like this. So, whenever this is there, then remove lighter, then make cigar, then smoke, and that is in an infinite loop, fine. So, similarly, smoker 2, that particular code is like this. So, this will be while true, wait on tobacco, semaphore. Now, remove tobacco, make cigar, rest of the thing is similar, make cigar and smoke. Similarly, you can write the code for S3. So, S3 code will be like this. while true, waiting for this paper, semaphore, then remove paper, then make cigar, then smoke. So, these processes are more or less similar. So, 3 smoker processes are quite similar. What about the agent? Okay. Agent. So, agent is also in a infinite loop. This is not while so it has to randomly pick up one such item. So, item it has to pick up randomly from lighter, paper and tobacco. Now, if item is equal to lighter, then it has to give that it has to signal lighter semaphore. Okay. Similarly, you can write other 2 ifs. So, if item equal to paper, then signal paper semaphore, the item equal to tobacco, signal tobacco semaphore, like that. Now, after that, so it has put it there, then after some time either it is taken up by some of these smokers, or it has to repeat. So, this whole thing must go on. So, this so again this is in an infinite loop. So, it has to go back there. Okay. So, how it operates? So, these 3 semaphores that I have, that is this paper semaphore. So, this paper semaphore, so this is initialized to 0, then this lighter semaphore, light semaphore, so that is initialized to 0, and this tobacco semaphore, so that is also initialized to 0. All of them are initialized to 0. So, initially if any of these S1, S2, S3 they are scheduled, so they will get stuck at the corresponding wait statements, okay, because none of them will be getting anything. So, now once the agent process is scheduled, so agent process it will be getting it will be picking up randomly one of the item, and based on that it will be making one of the semaphore variable to be equal to 1. So, maybe it will make the picks up the lighter. So, the lighter is made equal to 1. So, P1 the S1 was waiting at this point. So, S1 will be signaled and it will remove the lighter and it will take it. Okay. So, that similarly next time, so once it executes this wait, so this will become 0 again and it will go on like that. So, next time this agent comes, so agent will be again picking up one item that way, and it will be maybe this time puts paper onto the table. So, makes this semaphore to be equal to 1, and then this S3 will get a chance for execution. So, S3 will make this it will execute this wait. So, it will make it back to 0 and then it will do the cigarette and smoke. Okay. Now, the question is this a correct solution? So, apparently it seems that it does well, but there is a catch here. Like suppose it happens like this agent process. So, agent process it executes one loop of this statement, accordingly it has picked up a lighter. So, it has made this lighter semaphore value equal to 1, fine. Now, before this lighter is so before this process S1 is scheduled, suppose this agent is scheduled once more. So, one thing you remember that we said that there is no assumption regarding relative speed of execution of the processes. Now, it may so happen that before S1 is executed, this agent executes once more. So, as a result, what happens is that this agent will be putting another item onto the table. So, and how will it put it? So, it will make this one of this semaphore to be equal to 1. So, next time it may be making this paper semaphore to be equal to 1, or it may so happen that in this random choice process it picks up lighter again, and as a result this lighter semaphore becomes equal to 2, whereas rest of them remains 0. So, this can happen. So, these semaphore values, so due to this relative speed problem, so it may so happen that after some time there may be a number of items accumulated on the table, because the corresponding smoker processes they did not execute in between. Okay. So, if the agent is executing at a high speed, and as a result this agent has piled up lots of items onto the table, and then these smoker processes come and they find the items are available on the table by means of the semaphore variables having some large value more than 0, and that way all the processes will go into their critical section, which is basically making the cigar and smoke. So, it will be the critical section. So, they will be going into their critical section simultaneously. So, to avoid this situation, one possibility possible solution is that this agent before starting the next iteration, it must be told that the item that it put on the table has already been consumed by one of the smokers. So, this table access is an important issue. So, we can say that we can have another semaphore variable called table, which is initialized to 0, and so that this after putting this agent process, so at the end of it, so it should wait on this table, it should wait on this table, and after removing the paper here, so this at this point there should be a signal table here. Okay. And obviously, there is another issue, like say if this removal of paper, or that is when this agent process is putting something onto the table, and at that time if these smokers they come, so they are trying to access the table. So, we should be able to protect that, and of course, that will be ensured automatically, because now if the agent comes, so it executes this code and it waits for this table variable is initially 0. So, one of these smokers will be scheduled. So, they will be once that is done, so they will be doing this signal operation, signal on this table. Similarly, here also I should have a signal on table. So, this will be executed, and once this signal is executed, that means the item has been taken by one of the smokers. Now, this agent will be through this wait statement, and it can go back and execute this while loop again, and it can it will be able to get the item from the table and put the next item onto the table. So, this way we can have this process synchronization type of problem modeled by means of these semaphores. Okay. So, another typical example that we can think about is like this. Suppose I have got a set of equations, and suppose I have got a set of simultaneous equations. Suppose there are 3 variables x1, x2 and x3, A11 x1 plus A12 x3 equal to B1, then A21 x1 plus A22 x2 plus A23 x3 equal to B2, and then A31 x1 plus A32 x2 plus A33 x3 equal to B3. Now, you know that there are many numerical methods by which we can solve these equations, like this x1 can be obtained from this equation 1 by A11 into B1 minus A12 x2 minus A13 x3. So, from the first equation we get x1, from the second equation we get 1 by A22 into this value. Similarly, x3 is 1 by A33 into this equation. And the way this numerical solution methods work is that they assume some initial values of x1, x2, x3, and then these equations are used repetitively to get new values of x1, x2, x3 until and unless the values converge to some value. So, there is an epsilon the error margin. So, that in the previous iteration whatever were the values of x1, x2, x3, in the next iteration if the values are almost similar to that and the error margin is less than epsilon, then the iteration stops, otherwise it goes on doing this thing. Now, here you see that one thing is that suppose I have at present I have got current pair of current triple of these values x1, x2 and x3. So, that triplet it will be used for getting the next one. So, x1 dash, x2 dash, x3 dash. So, if I say that x1 computation, so this is done by process P1, x2 computation is done by process P2 and this x3 computation is done by process P3, and there is an update process, which covers which copies this x1 dash, x2 dash, x3 dash into the x1, x2, x3. So, that next iteration it can use this. Now, this process P1, that if you try to look into this process P1's code, so it will be having this computation for this equation 1 x1 equal to etcetera. Okay. After that it should wait for it should do a signal on some semaphore x1 updated, and then it wait for another semaphore which is full update. Similarly, P2's code will be like this. So, this is x2 equal to something, and then it should signal x2 updated, and then it should wait for full update, and then this will continue, this will go in a loop. Similarly, the P3 code will also be similar to that, signal x3 update, and then it should wait for full update, then it will do the next operation. Then this update routine. So, update routine may be like this. So, update routine, so it should wait for this x1 update on this semaphores x1 update, it should wait for x2 update, it should wait for x3 update, and then it should do the update operation, which is basically copying the x1 dash, x2 dash, x3 dash into x1, x2, x3, update all, and after that it should give this signal full update. It should give signal full update, and this signal should be given thrice because all 3 processes are waiting for this. So, I have to give this full update thrice. So, that all 3 of them will be, or better I should say this is I should say full update 1, full update 2 and full update 3, and accordingly it should give signal full update 1, signal full update 2 and signal full update 3. That will be a better approach. So, what I am doing? I am having a number of semaphore variables x1 update, x2 update, x3 update. So, all of them are initialized to 0. So, that even if the update process comes first, so it will be waiting on these, and then when P1 is over, so it is giving signal x1 update. So, this this will be through, then this will be through, this will be through, then update process will update everything, then it will signal full update 1. As a result, P1 was waiting at this point. So, P1 will know that update has been done. So, P1 can start its next iteration. Similarly, by this signal, so P2 will know that this is this update is over. So, this update has been done. So, it will be doing this thing again. It will go to the next iteration of this statement. Similarly, full update 3, signal full update 3. So, it will be getting this full update P3 will be getting the signal, and it will start the next iteration. So, in this way the synchronization problems we can solve using semaphores. So, we will be looking into more classical problems in the next class.